All right, so let's go through the solutions to the optional exam. And for this one, we have a differential equation. dy over dx is 2 minus y over x. I'm sorry, y was dark. I don't know. And then we have to draw the slope field at those 9 points given. So I'm going to actually switch screens here a little bit so I can draw directly on this. And so they give us the differential equation, again, 2 minus y over x. And so what we have to do is take each x and y coordinate given here and plug them in and get the slope, and then draw a little segment with that slope. Now, the easy thing here is if y equals 2, then dy over dx is going to be 2 minus 2 over x, which is going to be 0 over x, which is going to be 0 because x is positive here. So that means right along y equals 2, it's going to have horizontal segments. And then in the grading of this, or the scoring of this, they give 1 point for the slopes, the line segments with 0 slope. So that's 1 point right there for just getting that. The other point, because this is a 2-point question, comes from the rest of the line segments. So you can make a little table if you want. They didn't ask for a table. So, if you put your point here and then your slope over here, that might help you stay a little more organized. So when you're at 1, 1, you're going to plug in 1, you're going to get 2 over 1, which is going to be 2. When you're at 2, 1, you're going to plug in, you get, did I do that right? I didn't do that right. I'm sorry. When I plug in 1, 1 to the first one, 2 minus 1 is 1 over 1 is going to be 1. I'm going to get 2 minus 1, which is 1 over 2 for the second one, so 1/2. And when I plug in 3, 1, I'm going to get 1/3. And so what you want to show here is you want to show not necessarily precise slopes, but a trend, okay? So at 1, 1, you have a slope of 1, and this one you can line up pretty well here. But 1/2 is less steep, and then 1/3 is less steep than that. And that's what they want to see. They want to see the slopes getting less steep from left to right for this example. They're not going to be measuring. They're going to say, is the first one reasonable? Is it close? And then do the others follow the correct pattern, like they're getting smaller, like they are? Okay. Let's see. Now we get to point 1, 3. Whoops, 1. 1 comma 3. That means I'm going to put 3 in for y, so that means I'm going to get, I'm going to write this down because I don't want to screw this one up. Negative 1 over 1, which is going to be negative 1. And then I'm going to plug in 2, 3, which is going to give me negative 1 over 2. And then I'm going to plug in 3, 3, which is going to give me negative 1 over 3. So now I got negative slopes. Okay, so I got a negative 1. Whoa, what just happened there? Sorry, technology issues for old people. Okay, and then that's about negative 1, and then a little less steep like this. Okay, maybe that one should be a little bit more, look a little bit better like that. But that's essentially what you're trying to do for that problem. Okay, so again, 1 point for the 0 slopes, 1 point for the other ones, and you're just trying to become reasonable and that they follow the correct trend in the way things are supposed to go. All right, so that was part A. Let's get on to part B. Let f of x be the particular solution to the given differential equation with the initial condition f of 3 is equal to 1. Write an equation for the tangent line, which we've been doing for a long time. So the graph of y equals f of x at x equals 3, and use the equation to approximate the value of f of 3.5. So, okay, we have our differential equation, and we're using the point 3 comma 1. So it means I need to find the slope, and so I need to plug in 3 comma 1 for x and y. And in fact, I just did that, didn't I? Over here, when I plugged in 3 comma 1, I got 1/3. Okay, so I'm going to use that result. And then the equation of the tangent line is going to be 1/3 times the quantity x minus 3 plus 1. And so f of 3.5 is going to be approximately, don't put an exactly equal to sign here, Sometimes they'll deduct that because you don't understand that you're approximating. At least they don't think you understand that. And so I don't want you to be penalized for not doing that part correctly. You don't need to simplify, ladies and gentlemen, so you can stop right there if you want. But if you want to keep going, you can. So this is 1/3 times 1/2. 3.5 minus 3 is a half plus 1. So it's 1/6 plus 1, which is 7/6, so 1.1666 repeated if you want to do all of that stuff. Let's take a look at the next part. Part C. Find the particular solution y equals f of x to the given differential equation with the same initial condition f of 3 is equal to 1. So we have dy over dx is equal to 2 minus y over x. And again, we have f of 3 is equal to 1. So the problem that a lot of you had here was in finding the antiderivative of the 1 over 2 minus y part, but I'll talk about that in just a moment. When we separate the variables, we're going to move this term over here like this, and then that x is still in the denominator. There was a couple of you who decided to leave or somehow put the x in the numerator, which then screws everything up. Okay, so now we need to integrate. 1 over 2 minus y dy is equal to 1 over, the integral of 1 over x dx. Now, to find the antiderivatives in this, they try to be a little bit tricky to see who's paying attention and who can do these things accurately. This minus sign in front of the y is something that a lot of students don't account for properly, and then they have you. You're going to be wrong, and you're going to lose a whole bunch of points because you're not being careful. So do a substitution here. So let u equal 2 minus y, so you can do this so you can see what's going on. Then you're going to get negative dy over here, like this. And so you got to balance out the dy with a negative du, which a lot of you didn't do, and then that caused all kinds of problems. So you get negative 1, integral 1 over u du over here. Still got the integral of 1 over x dx over here. Now this becomes negative natural log of the absolute value of u. This over here becomes the natural log of the absolute value of x plus c. They sort of form the problem in a way that if you ignored the absolute value, you wouldn't be too heavily penalized or at all. They could make it so that you have to deal with the absolute value symbols better, but my advice is just to be careful with these things. So we have this, and we know f of 3 is equal to 1, so let's go ahead and substitute in there and see what's going on, or figure out what c is. So then I'm going to plug in a 1 for y, so 2 minus 1 is 1, so that's the absolute value of 2 over there. I'm going to plug in 3 for x. I don't need absolute value symbols anymore. I'm talking too much and not thinking. That should have been the natural log of 1. Natural log of 1 is 0. The absolute value of 3 is 3. So c is the negative natural log of 3. And so when I substitute it back in for c, we get this expression here. And now we just got to solve for y. Now to solve for y, what you want to do is let's get rid of that negative first. There's a way of not getting rid of the negative first that works out okay. I just don't advise that you do that. Whoops. Sorry. Computer issues. I don't know what happened to part of my screen here. All right, there we go. This was a minus sign originally. Now it's going to be a plus. All right. Now you get the absolute value of 2 minus y is going to be equal to e to the negative natural log of the absolute value of x plus natural log of 3. Now that's actually going to work out kind of nicely for us here. This is going to be e to the negative natural log of the absolute value of x times e to the natural log of 3. And I'm a little sort of not confused. I want to know what the next best step is, and I should have thought of this ahead of time. This part's going to become 3. Okay. Now this part over here is, you can't just cancel the e in the natural log because it's negative. You got to move the negative on the inside. In case you don't remember, if I take um, the natural log of x to the power of a, that's the same as a times the natural log of x. So the exponent became a multiplier. So I can reverse that. I can move the multiplier into an exponent position. So this could be e to the natural log of the absolute value of x to the power of -1. And all this is still times 3. Something to the power of -1 is just a reciprocal. So this is absolute value of 2 minus y is going to be equal to, the e in the natural log will cancel here, and I'm going to end up with 1 over the absolute value of x times 3. All right, which I'm going to write as 3 over the absolute value of x. So now I'm going to drop the absolute value symbols and put a plus or minus in front, so we can account for all the different ways that might work out. So the negative y is going to be equal to -2 plus or minus 3 over x. Y is going to be then +2 minus or plus 3 over x. And then we just got to choose the right point. Remember, it was s at the point 3 comma 1. So if I plug in 3, I got to get 1 as the y value. Now if I plug in 3 for x, then I get 3 over 3, which is going to be 1. So I want to subtract 2 minus 1 in order to get this 1 right here. If I use the plus, I'll go 2 plus 1, which will give me a 3, and my y-coordinate's not 3. So I want the subtraction. So it's 2 minus 3 over x is what y equals. And there it is. Again, they made it so that if you didn't account for the absolute value symbols the way I did, you'd still be okay. I just like to do things more precisely mathematically. All right, for the second question, we got this graph here. The continuous function f is defined on the closed interval -5, 5. The graph ff consists of a parabola and 2 line segments as shown in the figure above. Let g be the function such that g prime of x is equal to f of x. Part A says to fill in the missing entries in the table below to describe the behavior of f prime and f double prime. Indicate positive, negative, or 0 and give reasons for your answer. Let me switch screens here so I can draw on this. So if we're looking from -5 to -3, that's this interval right here. So we see that f is increasing, so that means its derivative is going to have to be positive. So I'm just going to leave POS in there. And then from -3 to -1, we see that f is decreasing, so that means f prime is going to be negative. From -1 to 2, again, we're back to having f increase, so I'm just going to leave the p. Oh, I erased the wrong part. Okay, won't let me just draw over it. And then from 2 to 5, decreasing, so it's going to be negative. Now, what about concavity? Both of the end intervals are straight lines right here, and lines have no concavity. Okay, the second derivative, so the second derivative is just 0 on both of those. Another way of thinking about it is that the derivative of a line is a constant, and then the derivative of a constant is 0. You can think of it that way as well. In the middle here, the graph is concave up, so that means this is going to be positive for both. Now you're supposed to write reasons for your answers. Now, I'm going to use my teacher prerogative and say, I said my reasoning out loud for you to hear. I'm not going to write it down. Okay, but again, I'll just repeat it really quickly. Where f is increasing, f prime will be positive. So that's the -5 to -3 and the -1 to 2. When f is decreasing, f prime is going to be negative. That's from -3 to -1 and 2 to 5. And then for f double prime, when f is concave up, f double prime will be positive, and that's from -3 to -1 and from -1 to 2. And then in the linear portions, f double prime will be equal to 0. All right, let's go back to the picture. Here it says, in part B, there is no value of x in the open interval negative 1, 5, at which f prime of x is equal to f of 5 minus f of negative 1, or 5 minus negative 1. Explain why this does not violate the mean value theorem. So a lot of you, I think, didn't understand how to answer this question. You've never, I guess we've never gone over anything like this, and so be it. I'm glad we're doing it now before the AP exam instead of during. The mean value theorem, if the conditions are true, which I'll get to in just a moment, would say that there has to be some number, if the conditions were true, such that the slope at some point is going to have to be equal to the average rate of change on the whole interval. But here's the issue. You got to meet the conditions of the mean value theorem, and there are two. The mean value theorem says if f is continuous on the closed interval, and f is, okay, and if f is differentiable on the open interval, and in this case we're looking on the open interval from negative 1 to 5, okay, and from negative 1 to 5 we see right here there is a sharp turn, okay, and because of that sharp turn, f is not differentiable there, so the mean value theorem doesn't apply. So this doesn't violate the mean value theorem because the mean value theorem can't be applied when the function on an interval in which the function is not differentiable. So that's the answer to that question. I believe it's just a 1-point question, so you just had to be able to recognize that mean value theorem can't be applied here, and so that's why there's no contradiction, or it doesn't violate, as the phrase, to use the phrase they used. For part C, it says find all values of x in the open interval negative 5, 5, at which the graph of g has a point of inflection. And so a point of inflection, just to go back for a moment, the graph of g, we're looking at g prime is equal to f, okay? So let me get a screen here. So they tell us that g prime is equal to f. Points of inflection occur when the graph changes concavity. We go find that by looking at where the second derivative is equal to 0 or undefined, okay? And then we got to test to make sure concavity changes around those points. So now f prime is equal to 0 when the slope of the graph here is equal to 0. Well, where's the slope equal to 0? That's at negative 1, okay? So this one here is at x equals negative 1. Now, where is f prime undefined? Well, that's where we have all the sharp turns. So that's going to be at negative 3 and 2, okay? So now we need to make sure that g double prime changes sign. So, I mean, you can set up intervals around these points to see what's going on. So you can go negative 5 to negative 3, negative 3 to negative 1, negative 1 to 2, and 2 to 5, and see what's going on here. But wait, didn't we already do this? Didn't we already see what f prime was doing around these points? F double prime, I'm sorry, g double prime, which is f prime, doing around these points. So from negative 5 to negative 3, we have, that's not what I want. We have that f prime is positive, okay? From negative 3 to we just got positive, negative. So we can see right there that the signs are changing for f prime, g double prime, and so we have points of inflection at those values. All right. So since g double prime, which is f prime, changes signs at these values, x equals negative 3, negative 1, and 2 are x values of points of inflection. All right, and then wrong graph, need this one. And then part D says, at what value of x does g attain its absolute maximum on the closed interval negative 5, 5. Some of you are still giving me reasons for the local extrema, not the absolute extrema. And so let's go take a look. So, we could use the closed interval method here. Okay. So we need to find where G takes its maximum. So I need to find where G prime or F is equal to 0. And where does F equal 0? Well, only at the endpoints. F doesn't equal 0 at any other point. Okay. So there are no critical numbers. Okay. So that means I only have to test the endpoints. But let's look at this a little bit more closely. G prime, which is F, is greater than 0, which means that G is always increasing. And if G is always increasing, then where's its maximum going to be? At the right-hand endpoint. So whatever it is at negative 5, it's going to start increasing after that. So G has its absolute max at x equals 5. And there you go. That should do it.